Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on S parameter. So for this video, I'm going to derive the equation of the power wave of S parameter. The power wave is also known as the normalized wave. So basically, this will be the objective of this video. Guys, if you're keen to know more about S parameter, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion of S parameter. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel. Help me press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's take a look on this one-port network. So from here you can see that this will be the voltage, terminal voltage, and also the terminal current for this one-port network. We also have the incidence and also the reflected current and voltage. From here you can see that this is actually from the incident voltage. This is actually the incident current. Same over here. This will be the voltage of the reflected. This will be the current of the reflected. So the instantaneous one-port terminal voltage and current, they basically will be related to the incidence and reflected voltage and current component by this equation. Let's take a look on this set of equation. You can see from here, the voltage is actually all in series. So therefore, V1 is equals to the V incidence plus V reference. So this is the first set of equation. As for current, you can see that the incidence current is actually opposite with the reference current. So therefore, I1 is equals to I of the incident minus I of the reflected, as you can see from this equation here. Next, let's consider the case of a transmission line. So basically, this will be a transmission line. They have the characteristics impedance of Z0. So then the incidence and reflected component, they are actually related to this characteristics impedance by this set of equation. So you can see from here, this is actually the voltage of the incident over the current of the incidence. So from here, you can see that they are actually having the value of the characteristics impedance of the transmission line. Same for the reflected. So from here, you can see that this will be the voltage for the reflected divided by the current of the reflected. They were also having the characteristics impedance of the transmission line. So later on, you will see that I need these two set, and also this set of equation to derive the power wave of S parameter. So these are the three formula that I mentioned on my previous page here. So I just put it here, for convenience, and later I can so-called reference to this set of formula. Let me continue. So basically, let me focus on this equation here. So this equation I rewrite. So this V reference, as you can see from here, this V reference is equals to I reference multiplied by Z naught. Then you can see from here, I actually replace the V reference with I reference multiplied by Z naught. So next, what I'm going to do is basically this I reference, I shift this to the left. Therefore, I need to shift my I1 to the right. So will be equals to I incidence minus I1. And you can see from this equation here. So Z0 will be still the same. So I actually done this part here. So next, I'm going to expand here. So the current incidence multiplied by Z0 and I1 multiplied by Z0. So from this equation here, you can see that this I incidence multiplied by Z0, this I incidence multiplied by Z0 will be equals to V, of the incident wave, and therefore I actually replace this with the V of the incident wave. The rest will be still the same. over here you can see that I actually want to combine these two together. So these two things combined will be equals to 2 voltage incidence. Okay, which means that I need to shift this to the left. So this will be equals to V1 plus I1. Okay, so basically I shift to the left. I just change the so-called sign. Instead of minus, they become plus, and therefore I get this equation. So once I get this, I can actually get the voltage of the incident wave. Okay, so I just need to shift 2 to the right, so will be divided by 2. And finally, I actually obtain the voltage of the incident with this equation. Okay, so next, I'm going to get the voltage of the refracted wave. Okay, so this equation you can see from here. Okay, I actually need to shift this V incidence to the left-hand side. So therefore will be equals to V1 minus V incidence. Okay, so this is what I have found earlier on. Okay, so this is what I found it earlier on. So I just need to replace this with this. So therefore I replace it. So over here I can see that, okay, so these are so-called the light term. Okay, so from here I can see that these two things will become half V1. Okay, as you can see from here, this minus will be affecting the whole thing. So this will be minus. So this will be minus I1 Z naught. So basically, this is another equation that I actually obtained for the V reflected. So next for I incidence, okay, so basically you can see that this I incidence from this equation here. Okay, so you can see that will be equals to the voltage of the incident divided by Z naught. So this B incident, I already found it over here. So I just need to do a divided by Z naught over here, and I rewrite this equation over here. Same for the current of the reflected. Okay, so basically I just need to do a divide by Z naught, and I actually rewrite the equation here. So over here you can see that I actually has 4 set of equation. The voltage of the incidence, the voltage of the reflected, the current of the incidence, and the reflected of the current. So I actually have these 4 set of equation. Okay, so these are the 4 set of equation that I derived earlier on. Okay, so what is actually a power wave? Okay, so the power wave are normalized version of voltage and current wave. Okay, so basically this is what it means here. Okay, but I know that it may be very difficult for you to understand this form here. Okay, so therefore I have another form to describe this. Okay, so we know that P is equal to V squared R. Okay, so basically this is a very simple so-called Ohm's law. Okay, so over here you can imagine that this is actually the incident wave. Okay, AN squared here. So if I'm going to get the AN, okay, I need to remove away the 2. So this will be B in. This one I need to take a square root. So therefore, it will be this equation. Can see over here. This will be the AN here. So now I need to replace them with AN. So therefore, this thing I need to square. So therefore, I have this B incidence. And this Z naught I need to square. So therefore, I have this term. Okay, so basically from here, you can see that this is actually the set for the incident wave and also the set for the reflected wave. So basically, this will be the power wave that is actually normalized, okay, version of the voltage and current wave. Okay, so as you can see from here, okay, so this S will be the S parameters will be equal to the incidence divided by the reflected wave, which we are going to take a close look later on this S parameter. Okay, so guys, okay, before I continue, okay, urge you to help this channel by like this video. Okay, when more you guys actually help to like this video will have a better chances to reach out to a larger audience. So guys, help me press the like button now. For those who are new and in fact you have learned something from this video, I urge you, okay, to help this channel by subscribing to this channel. Once again, thank you so much for strong support. Let's quickly understand. Okay, so the one port relationship, which I have explained early on, they can be easily extend to the two port network as shown, okay, by replacing the A and B. Okay, you can see that they replace the A and B, okay, by the column factor A and B. Okay, so these power wave factors are actually related to each other by an S matrix that contain 4 complex parameters, as you can see from this equation here. So from here, you can see that the one port relationship can easily relate to the two port network. Okay, in fact, it can be any M port network here. Okay, so basically this power wave A and B variables, they are actually defined as n order column vectors, and you can see from here. Okay, so all these set of equations, they are still relevant, okay, for M port network. Let's quickly understand some key concept of S parameter. Okay, so the S parameters are measured by sending a single frequency signal into the network. Okay, so basically we are going to send this single frequency signal into the network, and we are going to detect the amount of wave that actually exit each port. Okay, so basically you can see from here, this is the signal that we actually send. Okay, and we are going to study what will be the amount of wave that actually exit from the port. So basically this will be exit from the port. This will be reflected, okay, but you can see that they also exit from the port here. Okay, so the power, voltage, and current incident wave, they can be considered as wave traveling in both directions. Okay, as you can see from here, okay, so basically you can see that the power, okay, beside traveling so-called forward as an incident, we also have this reflected wave also. So this is what it means. So basically the wave traveling in both directions. Okay, so power, voltage, and current, okay, they can easily consider as wave traveling in both directions, as you can see from this part here. Okay, so I have already explained this so-called diagram here. So from here, I just want to quickly mention that this is what I want to mention here. Okay, so basically they can so-called understand them as a wave that basically travel in both directions. Is for a wave incidence on port 1, okay, so basically this will be a wave that actually incident on port 1. Some part of the signal will be reflected back. Okay, so this part will be reflected back. Okay, while some portion of the signal will exit at the other port. Okay, so basically this is what it means. So basically I have a source, which is the incident wave on port 1. Okay, I have some part actually reflected back out of the port, and I actually have also some portion of the signal actually exit at the other port of the device or DUT, as you can see from here. Okay, so S11 actually refer to the signal that reflected at port 1 for the signal incidence at port 1. Okay, so therefore the scattering parameter S11 is actually the ratio of two wave, okay, which is B1 over A1. Okay, so basically this will be the amount of reflected wave divided by the amount of the incident wave. Okay, so basically this will be the so-called S11. How to describe S11? Next, for S21, they actually refer to the signal that actually exit at port 2. Okay, so the signal actually exit at port 2 for the signal incident at port 1. Okay, we have this signal that actually incidents at port 1. Okay, so therefore the scattering parameter S21 is the ratio of two wave. Again, from here, you can see that this is basically the wave that actually exit from port 2, which is B2. So B2 over A1, this is what we describe as S21. Okay, so next, S22 actually refer to the signal that actually exit at port 2. Okay, the signal that actually exit at port 2, okay, for an incident signal at port 2. So basically we supply, okay, at port 2, and we are going to see what signal actually exit at port 2. So this is actually the S22. Okay, so S22 is very similar with S11. Okay, so but this time round, the source will be at port 2. As for S11, the source will be at port 1. But for this case here, S22, the source will be at port 2. Okay, so this S22, you can see that basically will be the ratio of two wave. Okay, so basically you can see that will be the reflected wave divided by the incident wave. So basically this is to describe S22. Same for S12, they actually refer to a signal that actually exit at port 1. Okay, for an incident signal at port 2, okay, how much actually exit at port 1. Okay, so how to describe this will be using this S12, okay, which is the ratio of this B1 exit at port 1 over the source, okay, which is at the A2. Okay, so basically this is a quick so-called understanding of this S parameter, okay, in the forward direction and also in the reverse direction here. Okay, so but you can see from here, okay, they are actually quite similar, S11 and S22, S21 and S12. Next scale, so it is possible for signal that actually exit at port 2. Okay, for example, a signal that actually exit at port 2, okay, they actually will be reflected off something, okay, which is external to the network, and they actually re-enter the system, okay, which means that they actually bounce off and then they actually re-enter into the system, okay, as a second input. Okay, so this will also experience its own reflection and transmission. Okay, but I just want to highlight this is possible. We cannot assume that this thing come out from port 2, they will not be reflected back. Okay, for this case here, you can see that there is a possibility that the signal will actually reflected and they actually re-enter into the network again. So basically, this is what you want to mention. Okay, so the S parameters actually depend upon the network and the characteristics impedance of the source and load, which is used to measure it, and the frequency that is actually used to measure it. Let me give you some example here. So if the network is changed, the S parameter change. Okay, it makes sense, right? If I change this network, okay, the S parameter will definitely change. If the frequency is changed, okay, the S parameters change because you know that S parameter is only valid at one single frequency. So hence, when I actually change the frequency, my S parameters will also change. Okay, so from here you can see that if the load impedance is changed, okay, if I change the load impedance, then the S parameter change. Why? Because of the reflected wave will be different. Okay, keep this in mind. Because you change your impedance load, so therefore the return wave will be different, and hence the S parameters also will change. If the source impedance change, the S parameters will also change. Again, all this makes sense because if we're going to change this source impedance, the whole S parameters will be different. Okay, so with this, I'd like to end my discussion. Okay, please help to like this video and subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.